Okay, so we have a problem right here. The problem is x squared plus y squared is equal to 1, and we would like to find dy dx. So this kind of problem falls into the category of implicit differentiation. And before we talk about this particular topic, I would like to review a little bit and make sure you understand how we do implicit differentiation. Now, a lot of people got confused in the implicit differentiation. They just think about, okay, I'm going to do the dy dx thing, but they don't understand why they do the dy dx thing. Okay, now, let's go back a little bit and understand a topic that you have learned already, which is called the chain rule. Let's do a quick review. Okay, what is chain rule? A chain rule, it's when you try to differentiate a function and it turns out that it's a function within a function, and you will have to do a chain rule. So let me give an example, such as, let's say f of x is equal to sine of x cubed, okay? And we ask, what's f prime of x, okay? And just to go, I'm just gonna tell you that the notation, another notation to annotate f prime of x, it's going to be we can say dy dx if we say y is equal to f of x. Okay, so they are basically the same thing. All right, so let's say f prime of x is equal to, well, if you look at this function, you will be able to tell that we actually have two functions. We have a sine function, and then we have a cubic function within the sine function. Now, how do we do chain rule? One advice that I always give my students is that you have to train your eyes to see that there are layers of functions. So the outer layer, okay, which will be the sine function, and the inner layer, it's going to be the cubic function. And when we do the chain rule, we will differentiate the outer layer, the outer function first. So we think about, hey, what is sine? What is the derivative of sine x? Then we will say it's cosine x. But but in this case we have x cubed right inside the sine function, we will keep it untouched. Okay, we will have that. But that's not it, because we have the inner function, so we will have to multiply by the derivative of the inner function, which would be 3x squared. Okay, now this is how we do chain rule, but now some of you may not realize, okay, I know how to do it, but I don't really understand why I'm doing it. So it goes to the understanding of what is dy dx and how is dy dx, okay, which is like the f prime, but we will use dy dx right here. How does dy dx relate to chain rule? So it turns out that dy dx is it can be expressed by something called dy du times du dx. Now look at this as like fractions. So dy over du and times du over dx. If you think about simplifying the right hand side of the expression, you would get dy dx. So these two sides are equal. Now we see something new right here. We see something called u. So what is the u doing here? Why do we have this thing called u? Now we can use this example to analyze what's going on here. Now we have f of x, okay, and it's called sine x cubed. But what we can do here is that let's go ahead and say u, it's a function, u, it's actually called x cubed. So we can replace x cubed with u, okay. Now this is the key part of the understanding, which is I see something weird. I see x right here, okay, I understand the variable is x, but I don't see any x right here. And this is exactly why we need to do chain rule, because you are differentiating a function that it's not expressed in terms of x. It is a function in terms of x. And therefore, we will go ahead and say, all right, we can do that. We can find out f prime of x, and now this is where the notation comes up big. See right here, dy du. So consider that my y, it's actually sine u. Okay? And dy du means we are going to differentiate sine u in respect to u. But that's not dy dx, right? dy dx is this. If I just do this part, it's just dy du, dy over du. So we need to do something else, which is du over dx, meaning that we are going to differentiate u in terms of x. Okay? Now, to spare more room, I'm going to go ahead and continue over here. Let me just rewrite this very quickly. And I want you to take a moment to look at this again. Okay? Times d over dx of u. Okay, I'm just going to use some parentheses to make it look a little bit better. Okay? Now, I really hope that you can see how this is analogous to this. dy du times du dx. Now, do we know what the u is? We do. We know what it is. Okay? And let's go ahead and do a little substitution right here, just on the right-hand side. Okay? On the right side of the equation. Right here, this part particularly, because we are differentiating this in terms of x, so we need to see x. Okay, this means that we are indicating x is our variable, and this one means that u is our variable. And now we can go ahead and differentiate this. This is simply cosine u, okay, and multiply by 3x squared. Okay, now we really want to use x as our variable. So therefore, we will substitute x cubed back to u right here. So we have cosine 3x, I'm sorry, it's going to be cosine u, it's x cubed times 3x squared. Or if you rearrange it, it's going to be 3x squared times cosine x cubed. That is our derivative. Okay. Now, why is this understanding important? Okay, this understanding is extremely important because, let's go to here. Okay. I'm going to explain to you along the way. We will find dy dx. So basically, we are differentiating both sides of the equation. Okay, so d over dx of x squared plus y squared is equal to d over dx of 1. Now the right hand side is very easy to handle. It's just going to be 0. Now the left hand side, it's going to be d over dx of x squared. Now that looks very nice because we are differentiating something in terms of x, and x is indeed our variable. Plus d over dx of y squared. Now we have something very similar to what we have seen earlier, right here. Right here. I mean, right here. Right here. That you are differentiating something that is supposed to be in terms of x, but in the function itself, you don't see x at all. And that is the reason why we need to do implicit differentiation, because what is implied right here, that y it's the y it's a function of x. That's what we're implying right here. So now that is very easy. That is simply 2x plus, now right here. This is the concept that we use over here in this example. We would say, okay, it's going to be 2y times dy dx. It's equal to 0. Okay. Now, how can you see this better? Look at this y squared right here. I'm going to use the space over here. Look at y squared right here. I want you to look at this y squared as if like this. I want you to see that there are two layers of function. We have the outer function, which is a quadratic function, and then y itself is a function, which is very analogous to this one right here. We have the outer function, like sine x, and the sine function, and then the inner function is our cubic function. So whenever we have two layers of functions, then we will have to use chain rule. And when y is an implied function of x, that's why we call it implicit differentiation. So let's go ahead and move things around. Okay, so 2y dx is equal to negative 2x. So dy dx is simply negative 2x over 2y, and the 2 got canceled out, so dy dx is equal to negative x over y. Okay, so this is how we do implicit differentiation. You have to have a strong understanding of chain rule in order to perform implicit differentiation successfully and meaningfully.